welcome back, welcome back, welcome back. I'm Miss Lisa, and this is my YouTube channel where we talk about everything I want to, science and math, and today we're talking about chemistry, and in particular water. So I brought my demonstration material here. No tasty. Water, do you know water doesn't have a taste for us, but it does for animals? Isn't that weird? So like when they're drinking out of puddles and, you know, the toilet, it has a taste for them. That's what I heard. Of course, I heard it on the internet, so I don't know if you can trust it or not. All right, so why are we going to do a whole chapter about water? Well, water is incredibly important. There'd be no life on this planet without it. You're made out of a lot of water. You're sort of like a water balloon. That's why you shouldn't jump off of something tall, because you might splat like a water balloon. But, so there's physics up here. Let me erase the physics. What do I do with the eraser? Oh, there it is. It's on the floor. Did I lose it already? All right, say goodbye to the physics. And let's talk about chemistry. All right, so water, I always say, is unimpressed Mickey Mouse. Because the oxygen is bigger than the hydrogens. And the oxygen is more electronegative, which means it's stronger to hold the electrons to itself more. So it gives it a partial negative charge. And how you write this is like that. It's sort of like an 8 with part of it missing, and you write a little negative up there. So because of that, the hydrogens end up with less time with the electrons, so they end up with a partial positive charge. So therefore it is a polar molecule, and one way that the polarity is represented is from the positive to negative, they'll draw an arrow. And I always remember that because the positive on the partial positive charge looks like an arrow tail a little bit to me. Like, you know, if you draw it like this, you could cross that and it looks right? And then like there's your negative right there, your negative sign and your positive sign. So you can kind of see those in it. When I was learning all of this, I had a really bad concussion, and nowadays they would have sent me home for a year, but back in the dark ages of the 80s, they just sent me home to school, seeing double and everything for months, and I had to make up little ways to remember everything. It works out great now that I'm a teacher, because I have little ways to remember everything. So, you know, as long as I don't get like brain problems from it. I have heard that you're more likely to have brain problems when you get old if you've had bad concussions. Right now my brain's all right. Maybe it'll stay that way. All right, so the water molecule. Now, I said there'd be no life on this planet without it. How come? Well, because water has this polarity, it's a solvent. It can tear things apart that are charged with its positive and negative end. So that's really important. It's really important that things get dissolved in water, like dissolved oxygen for fish to breathe, and dissolved minerals and nutrients for plants to take up in the water as they are taking the water out of the ground. And in fact, plants couldn't drink if water didn't have this shape. How plants drink is they don't have a heart or a circulatory system or a mouth or the ability to swallow or do peristalsis or reverse peristalsis, you know, the pinch that takes the food through your food tube. They can't do any of that. How they transport water is through what's called capillary tubes. If a tube is small enough, water can crawl up it just by its stickiness, just by its chargedness. It's the same reason why if you look at a little drop of water in your finger, it beads up. Water is so polar, it sticks to itself and beads up. And when it's in a thin tube, it makes a U-shaped called a meniscus. And see how it's starting to crawl up the sides? Well, that's how even great big sequoia trees, if water didn't have the shape, they couldn't drink. If they couldn't drink, they couldn't do photosynthesis. If they can't do photosynthesis, we have no oxygen. We can't live. So that is one of the reasons why there'd be no life on this planet without water being exactly how it is. Another one is that has to do with ponds. When water is most chemicals are most dense as a solid, medium density as a liquid, and least dense as a gas. Water's not like that because of this and its geometry. when it freezes and it gets into its crystal lattice, it does so in a way that leaves a little place in the middle with nothing there. It spreads out. It's like if you were with a group and you were all standing real close together. And then a teacher says, okay, everybody hold hands and spread out and make a circle. That's what water does. It spreads out and makes a circle when it freezes. And then there's that empty space in the middle, which makes ice, solid water, less dense than liquid water. So therefore, ice floats. So what? It's a big deal. Ponds, if they froze like regular chemicals, they would freeze from the bottom, and because then something would freeze and it would sink because it would be most dense, and it would freeze, and all the little fish would die flapping up top on a piece of ice, and there'd be no life. Because remember the food web and the circle of life from Lion King? You don't want me to sing that. It's all connected, and if all the oceans and rivers died because of freezing from the bottom up, we would die. There wouldn't be life on this planet. So instead what happens is the water starts to freeze up top, and if it's freezing down here at the bottom, it'll float to the top, and it makes a layer of insulation. And all of this stays liquid through the winter, and the fish are all happy through the winter and live till the next year. We have life on our planet. Water is most dense at 4 degrees, and so it sinks down 4 degrees, and then it starts going back up. Let's see, what else do I need to say about that? I don't think I do. I think that's it. Okay, so the water molecule is amazing. We wouldn't have life without it. It spreads out. Look at all the pictures in your book, or if you don't have a book, look on the internet to see how they do. Water beads up. It's also this beating up of water makes a surface tension. Water is so sticky. It sticks to itself so hard that it makes a tension, almost like a skin, on the surface of the water, and that's what bugs can walk on. So I do a lab with my kids where we get out Petri dishes. You know what those are, but you can do it with a saucer, a bowl, anything. And if you do it really carefully, you can get a needle, a steel needle, to float on top of the water. You have to do it real careful. You have to put it down flat, not at an angle, because that will break the surface tension, and you can get it to float on top. So if we were in class, we would be doing that, but we're distance. All right. The other thing is, related to its polarity and how sticky it is, water has what is called a high specific heat, which means it takes a lot of energy to heat it up, and then once it gets heated up, it holds the energy and doesn't release it very quickly. It has an extremely high specific heat. So if it didn't, there'd be what? No life on this planet. Why? It's because of this. Other planets, like our planet, they're not covered with water. Our planet is covered with water. We're a water planet. So during the day, the sun shines on the earth, but it's covered with water. And so most of the energy goes into the water to heat the water up. So that keeps our planet from getting too hot during the day to support life like most planets are. Then at night, we turn away from the sun, and most planets get so cold at night it doesn't support life. But instead, we are covered with these oceans that have been heating up all day, so at night they start releasing that heat back to the environment, and it keeps our world warm enough at night to live in. It's almost like it was perfectly designed that way, isn't it? It's really surprising and really fun. The more you learn about science, the more you learn how many factors there are that life is dependent upon. And it's just unbelievable to think that it all happened just at random. It's just amazing. All right, now what about evaporation? How does evaporation happen? Say you've got a little puddle of water. I lost my eraser again. I keep doing that. Okay, so you got a little puddle of water. I love talking about water. This is one of my favorite chapters. I just love it. Okay, so you got a little piece of water right here. Say it's on your skin. Okay, and it evaporates. Now, evaporation and boiling are two different things. For that drop of water to disappear, it doesn't have to boil, does it? what happens is the water molecules are here in here, and they're zipping around in their liquid form. And every now and then one will run into another one with enough energy that it pops it out of the water, and it goes flying off as a gas. And when it does, it takes energy with it. So evaporation is a cooling process because it takes energy with it. So what's the opposite of evaporation? I'll drink some of our display water while we think about it. It's condensation. So the opposite, here I've got a glass, and it's got ice in it, and it's got some liquid. Okay, there's my glass. It's not a very good glass, but it's glass. Okay, and here comes a water molecule flying along with plenty of energy, flying along as a happy water vapor, and it hits this cold surface, and its energy gets sucked out into to help warm up this glass of delicious sweet iced tea. And it sticks right here, and it makes a drop of condensation on the outside. But as it does, it slows down where it can't go fly off as a gas anymore. Now it's a stuck little water molecule stuck on the side. And it gives its energy to the gas, and it's a warming process. And if you think about it, it makes sense. Someone has taken a shower at your house, and you didn't know it. And, you're walking through the house, it's one temperature, you walk into the bathroom where the shower was just taken, and there's all this water vapor, all this steam from that hot shower, and you walk in, and is it warm or cool? It's warm. Because as you go in, there's all that warm, steamy air, and then it's going to hit you, and if you're in there long enough, it might start condensating on you and giving you energy, and you can feel that heat. Okay, so we talked about ice, so I want you this week to look on the internet, look in your book, look at some ice, look at some snow microscopically. If you have a microscope and it's snowing where you are, this is January when I'm recording this, you could go out and maybe even look at it. I used to have in my science teacher books where it would get to this point and it'd say, go outside and get some snow and have your kids look at it. And I'm in Georgia, it snows once every 2 years. That lab never happened. If we even have a hint of snow, we send the kids home. We have snow days. So that was definitely a northern textbook. But if you're at home, being homeschooled, you can go out and maybe look at some snow under the microscope. It's really fun. Okay, so what is an aqueous solution? We learned, or maybe I think our next chapter is solutions. So what a solution is, technically, is a mixture that is the same throughout. It has the same color, taste, everything throughout. It doesn't settle out. In reality, we normally think of solutions as clear and it can be colored. So I always think of Kool-Aid as the best example of a solution. It tastes the same at the top, middle, and bottom. It's clear and it's colored. And I like black cherry best. That's my favorite Kool-Aid. I like it a lot. So what is an aqueous solution? It is a solution like Kool-Aid that has water for the basis of it that you dissolve other things into. And it's very important. A lot of our drinks are aqueous solutions, a lot of our cleaning things. Most things that you buy or most solutions you come in contact with are aqueous solutions. Aqueous means water, water-based solutions. Now, what is solvation? Let's talk about that. If you have a solution, you have the thing that gets dissolved and the thing that does the dissolving. The thing that does the dissolving is called the solvent. And I always tell kids to draw a big V. I don't know if you can see it on there. But write it with a big V and then fill it up with some water. So you can remember that the solvent is what does the dissolving. And it's often water. Water is called the universal solvent because it can dissolve so many things. It can't dissolve everything, but it can dissolve a lot. And what gets dissolved is called the solute. The solute. It gets dissolved. So in our example, water is the solvent, Kool-Aid, and sugar are the solutes. Now, solvation, if I had thing of water and I put salt in it, and imagine that we can see a salt crystal really big like that, the water molecules will line up with either the face of Mickey Mouse down or the ears of Mickey Mouse down, and they will attack the sodium chloride crystal. Sodium is positive, chlorine is negative. So the face will attack the sodium. So here's my sodium. And the ears of Mickey Mouse will attack the chlorides and will pull it apart. It will dissolve it. It will cause solvation. You can hear that word dissolve in that. So you can see that illustrated in your book. Now, electrolyte and non-electrolyte. There's a REM song about electrolyte. So electrolyte, pause, anticipation. An electrolyte is a liquid that has charged particles dissolved in it. So just like how sodium and chloride are charged particles, if I make salt water, I've made an electrolyte. Now, electrolytes can conduct electricity. And so, Gatorade. What? So Gatorade was made at the University of Florida Gators. Oh, don't they do that? I'm not big into football one way or the other. None of the colleges I went to really had much of a football team. I went to Erskine. They had soccer. I went to Georgia State, and they didn't have football at that time. Later they got it, but it was after I was gone. So never really got into college football that much. So anyway, Florida Gators, people were into that football team a lot down here in Georgia. And they, sometimes if you drink pure water when you're really hot and thirsty and sweaty, you'll just barf it up. Your stomach, your body likes to have the same amount of salt throughout. It's called isotonic, not hypertonic or hypotonic. They want it isotonic. The same salinity, the same amount of saltiness as your tears is what your body would prefer if you gulp down a bunch of water real fast. Otherwise, it has to do osmosis a lot of times to even out the salinity. So sometimes your body will be like, nope, too hot, too sweaty, can't deal with that pure water right now, and barf it up. So at the University of Florida, they said, we need something that is more isotonic, iso meaning same saltiness as what's in your body. It says that the kids can just gulp down if they're really hot and thirsty and not throw it up. That it would have electrolytes in it. That it would have the same salinity, the same saltiness. So I don't know if you've ever noticed it, but Gatorade is sweet, but it's salty too. So, and you can chug it while you're hot and you will not throw up. And that's why the football players all have it. They dump it on the coach's head. It's all because of that. So if you look at Gatorade, it's got a big G and it's got a lightning bolt on it. And it's because electrolytes conduct electricity. And that's where Gatorade. So Gatorade's our electrolyte we can think of. Now, suspension colloid. Remember how I told you that when you say solution, it is usually what you think of as clear, but it can be colored. Now, technically, something could be cloudy, but usually when chemists use the word solution, they're talking clear. But technically, it could be cloudy. If it's cloudy throughout, like milk, that is called a colloid. That is where it has particles that make it cloudy, like the fat and things like that make milk cloudy, but they are not so heavy that they settle out. If they settle out, it's not a colloid, it's a suspension. And sometimes they have suspensions now. There's these things where they can make fibers go through the liquid, and you can have bigger chunks that would have settled out, not settle out. And that's what the bubble tea is. You know how you can buy that bubble tea? It's the rage around here, Marietta Square here, we got a bubble tea place. I've never tried it. I guess I should, but I don't really live close to Marietta or any bubble tea place. I live more out in the country, and we don't have bubble tea places out here in the country. You'd have to go to the city for that. Now, how can you tell if it's just barely cloudy? How do you tell if it is a colloid or a regular solution? What you do is you shine a light through it. And if you can see the sunbeam, the light beam, then it's a colloid. So what we would do if we were in class, I've got this really old film strip projector. Ask your parents, they might know what it was. You'd go beep and you'd flip it and you'd see a film strip. But it's got a really bright light, and it's really good for holding up the test tube and seeing if it makes the beam of light. If it does, it's a colloid. And that, the scientist who figured this out was Tyndall. So it's called the Tyndall effect, which I always feel like, and it's just that if you see a beam of light, how you can see, like in your house in the winter, there's this late afternoon beam of light coming, a sunbeam coming in your living room that you thought was really clean, but you see all this dust floating in the air because of the Tyndall effect. I always feel like there were certain things in science I could have thought of, and I feel like I could have thought of that one. A lot of things I couldn't have thought of, but I really think I could have thought of the Tyndall effect. Anyway, what about soap? Soap and detergents, how they clean is they have a polar end and a non-polar end. And you can read in your book and see the difference. Or you can look it up. But you can think of them as a fish hook. And this end of it is non-polar. It is not charged. And it turns out in chemistry that like dissolves like. So here you've got some oily dirt on your arm, and the soap will stick the non-polar end in the oil. This end up here is polar. So it's got a non-charged end and a charged end. The polar end sticks out, and the water molecules come and happily stick themselves to the polar end and pull it away. And then that takes the oily dirt away, and you get clean in your bath. One time, a long time ago, I had a student come up to me, and so I always say, so water without soap doesn't work, and soap without water doesn't work. You have to have both. And I had a student a long time ago say, Miss Blackburn, I never use soap. All I do is get in the water and let it run on me, because she was afraid of letting her skin dry out. And I don't know, she didn't seem real stinky, so she seemed pretty clean. So I don't know. Sometimes our bodies are amazingly made where they can do things, so maybe we really don't need soap. I don't know. That's just how soap works. You can read about it. Okay, there's another thing called that is called the water of hydration. And what it is, and we would do this in lab if we were together, but there are, remember when I talked about crystal lattices, and we're just going to represent the crystal lattice as a checker grid there. There are chemicals that make ionic bonds, but they do so in such a way that there are these spaces in the middle. And sometimes water molecules will fit themselves into those spaces. It is called a hydrate compound. And the water molecules are not bound into it. It's not a chemical bond. They're not really part of the crystal lattice at all. They just found a little place to be in the crystal lattice, and it's called a hydrated compound. And a lot of times it will have the formula like copper chloride, and then it'll have dot 6H2O. That means for every copper chloride, 6 waters are stuck in the crystal lattice. In chemistry class, what I do with the kids is we put one of these hydrates in an evaporating dish and put it in the fire and see what happens. And what happens is the water comes out of solution. It becomes steam and comes out. When it does, it pops sometimes, so they have to put a watch glass on top of it so they don't get popped by a hot exploding crystal. But the color will change. So like these are pretty blue crystals, and they'll turn whitish gray. And then you add water back to it. After it's all cooled, you can drip water back in, and chink, it turns back blue again. So that's something probably you can't do if you're just doing this class at home. But I bet you can find it on the internet. I bet you anything. There's a video of somebody doing that. All right? So that is chapter 16. Like, share, subscribe, and I'll see you next time.